Topic 1.6 notes, lesson 1. What is a system of equations and how do we solve? So the first page of the notes is a whole bunch of emoji puzzles. And the reason that they are on the first page of the notes is because they are a visual representation of systems. So what is a system of equations? A system of equations is when you have an equation that has two unknowns and a second equation with two unknowns, and you are looking for the solution that satisfies both of those equations. So if you look at the first emoji puzzle, you see that all three of the emojis in the first equation are the same image, and they add up to 24, which means each of those would be 8. Well, then you can carry that 8 down to the second one. 8 and 8 is 16, which means that the first emoji has to be 2 so that you get a total of 18. We know this is 8, right? And so when you subtract 8, subtract what is 2, well, then that would mean that these two represent 6, which means one of them represents 3. So now we get to the bottom one. This represents 2. We began with that representing 8, and that represents 3. So 2 plus 8 plus 3 is 13. Why does this represent a system? Because the emoji with the sticking out the tongue there represents an 8 in every equation that it shows up. Same thing is true with the emoji with the glasses, and the same thing is true with the smiley one. All right, number 2. Why don't you try that one and pause the video and try it and see if you can figure out what the answer is in the fourth line. Okay, each of these are 10 because that adds to 30. So that means this is 10. So 10 from 18 is 8, which means each of those are 4. We know that's 4 subtract 2 equals 2. So that means one of those is going to be 1. So 1 plus 4 plus 10 is 15. Did you get it right? All right, for number 6 here, each of these are going to be 20. That's 20, which means that's 5 and that's 5. That's 5. Subtract 2 is 3. That means that's 1. We said that was 5, and that's 20. Now, what's unique about this one is that you have to pay attention to order of operations. There's a dot in between those two, and so you have to multiply those two, so that's 100. So the answer to this is 101. Number 3, why don't you try that one? So pause the video and see if you can get it right. All right, so I think that one is 16. Okay, so we're going to have 8s again. So again, you can pause, see if you can get it right. These are great puzzles. All right, so for this one, we would know that this plus this equals 30, right? So if you add them, they equal 30. and if you subtract them, they equal 10. So add, they equal 30. Subtract, they equal 10. So that means that one of them is 20. So that means this one is 20 and this one is 10. Is that right? 20, 10, 38. 20 minus 10 is 10. That means that's 20. That's 10. And we said that one was 8. And again, now you're going to multiply. And so that's going to be 80 plus 20, which is 100. So that one was a little more challenging. Last one. Go ahead, try it, and then unpause the video and see if you got it right. So each of these has to be 10 to add up to 30. That's 10. 20 subtract 10 is 10, so that's 5. That's 5. That's 5, 6, 7, 8, 9. That's 2 for 2 of the spark plugs, so that's 1. This is 5, and this, we said, was 10. But you have to pay attention because of this multiplying. So 10 plus 5 is 15. All right. How do we know if we have a solution to a system of equations? So given number 1, how do we know that 3, 1 is a solution to the system? Well, we plug 3, 1 into both equations. So that's going to be 3 times 3 minus 4 times 1 equals 5. So that's 9 minus 4 is 5. That checks. 3 plus 7 times 1 equals 10. That checks. So yes, that means 3, 1 is a solution to that system of equations. One way to solve a system is to solve it graphically. Where the two lines meet will be the solution to the system. So you'll graph the lines. If they aren't in slope-intercept form, you have to rewrite them to that form. You determine the intersections of the lines, and that point is called the solution. Now, if the two lines do not intersect or they are parallel, we say they have no solution. Okay? If the two lines are the same line, they have infinitely many. All right, so we're going to graph these to determine what their solution is, and we need to first put them into the correct form, which is slope-intercept. So with the first one, we're going to write that as 3y equals negative x minus 9. We're going to divide by 3. And we're going to get y equals negative 1/3 x minus 3. For the second one, negative 3y equals negative 2x. We're going to divide and get y equals positive 2/3 x. So we're going to go ahead and graph both of those lines. So down here at negative 3, it has a negative 1/3 slope. So up 1 over 1, 2, 3, up 1 over 1, 2, 3. All right, so we're going to be able to draw this line. No, that is not a good line. Let's try that again. That's a little bit better. All right, then we're going to draw the second line. Goes through 0, 0, and it has a positive 2/3 slope. Up 2 over 3, up 2 over 3. And now I'm going to draw that line. And we can see that the two lines are intersecting at that location right there. That is the solution to that system. And that is the ordered pair, -3, -2. Okay, for the second one, we are going to do the same thing by putting both lines into the correct slope-intercept form. All right, so as we said, we're going to get them into slope-intercept form. So the first one is going to be -2y equals -x minus 2. Dividing everything by -2, that line becomes y equals +1/2 x plus 1. So that is one line we're going to graph. Over here, we're going to subtract the -3x, so that's going to be -2y equals -3x plus 2. Dividing by -2, that line is going to be y equals +3/2 x minus 1. Okay, so we'll start with the first line. Y-intercept of 1, up 1 over 2 for the slope. So I'm going to draw that line. Make it as straight as I can. Second line goes through -1 for the y-intercept, up 1, 2, 3 over 2. So it's pretty clear right away to see where the two lines are meeting. And they are intersecting at the point 2, 2 in the first quadrant. Okay, so notice that both of these systems, the lines intersected. And so if we go back up here and revisit our one solution systems, we would call that system consistent and independent. That would be the type of system that it is. If the lines are parallel, where we said there's no points in common, no intersection, we say that's an inconsistent system. And then if you have the same line, if you graph it and the one line sits on top of the other, all the points are solutions. And we say that is a consistent dependent system. All right, so let's review that. This is one intersection point, right? That solution is 2, 2, just like the one we just did. And that is consistent. Right, so if we go back up and look, that is consistent independent. And then for the same line, consistent dependent. And parallel lines, inconsistent. No solution. All right? So infinitely many solutions, and of course this one has no solutions. Now these are linear systems that have these three situations. We can also graph nonlinear systems. So what is a nonlinear system? Well, a nonlinear system means that when you go to solve it, you are solving where one of the equations is one of the parent functions that we've learned, absolute value, quadratic, cubic, all right? So we're going to graph just like we did before. Y equals x squared plus 1, that's your quadratic parent function with a transformation up 1. And if you want to be super precise about the graph, because we're looking for the point of intersection or intersections, you might want to plug a couple points in to make sure that it's accurate. So maybe plug in x is 1. That would put me up here at 2. -1 would also put me up there at 2. So there's my U-shaped curve. Now we're going to graph y equals 2x plus 1. So there's your plus 1 right there, up 1, up 2 over 1. So I'm seeing that these 2 points right here. Actually, let's see if I can get that line just a little bit straighter. There we go. We can see that that line is intersecting that parabola, that quadratic, in 2 places. So it says, what are the points of intersection? Well, 0, comma 1 and 1, comma 3. These are the solutions to the system. Now, a second way that we could do this would be to place it into our graphing calculator using the y equals menu. And a third way would be to solve it using algebraic methods that we're going to do later on. All right, let's try another one. What we have here is an absolute value and a line. Okay, so nonlinear. So our absolute value function has been translated 3 to the right. So that's 1, 2, 3. And then just to be precise with our graphs, we're going to find some points to plot so that we get it nice and accurate. V there. All right. And then we're going to graph the line y equals negative 3x minus 1. So we're putting it in slope-intercept form. So that's minus 1 with a negative 3. Up 3 over 1, up 3 over 1. And we're going to graph this line now. And we will see that the line and the absolute value function intersect right there. So the solution, there's only one to this. There could be more than one, but the solution to this system is the ordered pair, negative 2, 1, 2, 3, 4, 5. Negative 2, 5 is the solution to that system. Now we're going to move on to solving linear systems of inequality. So we're going to graph lines in the coordinate plane, and we're going to shade the solution set for each of them. And then we're going to look to see where all of the solution sets overlap, and that is the final solution set of the whole system. So instead of graphing and having one single solution, or infinitely many or none, now we're going to have an entire region of the coordinate plane. All right, and so we're going to graph them like we did in the prerequisite skills where we talked about graphing. So for the first one, I'm going to subtract the x over to the other side, and that's going to be negative y less than negative x plus 2. And when I divide by the negative, it reverses the inequality symbol, so y greater than x minus 2. So that'll be the first line that we graph. Down here at negative 2, we're going to go up 1 over 1, up 1 over 1, up 1 over 1, and it will be a dashed line. And then we will choose our test point to determine where we shade. Are we going to shade above that line or below that line? And that's all depending on where all the solutions to that linear inequality fall. So I will use my test point. I'm going to use 0, 0, okay? And so I'm going to plug in 0 greater than 0 minus 2. 0 is greater than negative 2. That is true. And so all of the points that lie in that region will be solutions. So you can either shade. I usually do arrows to point that the first set of solutions will fall on that side of the line. The other two lines are your special kind of lines, your verticals and your horizontal. So x greater than negative 2. So I'm going to actually use a different color now. I'm going to use gold or orange, I mean. Negative 2, and again, it's going to be a dashed line, but it's a vertical line. So when the line is written x equal, it's a vertical line. Where are all of the values of x that are greater than negative 2? To the right. So now you can see my arrows pointing to the right, x greater. Our third line, I'm going to choose a different color. This time I'm going to choose blue, is y less than or equal to 3. So 1, 2, 3, and it's less than or equal to, so now our line can be solid. And it's less than. So where are all the y values less than? So now you're going to see my arrows pointing below the line. And so now you have to figure out, where are all of those arrows converging? So they are converging, I'm going to color that gray, in this region right here. And so since you will be doing some of your work using Notability, I suggest that you do color coded. It's much easier for me to see the final solution. Okay, for the second one, you can go ahead and try it on your own. You can pause the video and then you can look to see if you got it right. So I graphed my first line, negative slope, again dashed. We determine our test point to decide if we're going to shade on the section below or above. For this one, again, it's kind of easy to use a test point of 0, 0. So there's my point 0, 0. So I'm going to test 0 less than 0 plus 3 is 0 less than 3. And yes, it is. 0 is less than 3, which means that all of the other points that represent solutions fall on that side of the line. Negative y greater than negative 2x plus 5. So I subtracted the 2x over. Now I'm dividing by a negative, so that reverses my inequality sign. So it goes from greater than to less than. 2x minus 5. All right, so I'm going to choose a different color to plot this line down here at negative 5. With a positive 2 slope, so up 2 over 1, up 2 over 1, up 2 over 1. And my line is dashed because, again, it is less than, not less than or equal to. Test point, I'm going to still pick 0, 0. 0 less than 0 minus 5. 0 less than negative 5 is no. So I will not shade on that side. I will shade on this side of the line. And so therefore my final solution is going to be this region right here. Many times I get the question, how do you know when to shade? Well, if you look at these, they all have inequality symbols in there. They do not have equal signs. And when we graphed equal, we got a single solution. When we graph with inequalities, we get an entire region of solutions. This is called the solution set. So that gray region. Okay, let's try one more. And then we're going to do a non-linear system. Okay, so for this one, we're going to be down here at negative 4, up 1 over 2, up 1 over 2. Again, you can pause the video and see how you do if you try it on your own, and you can just fast forward ahead and see if you are correct. This is a dashed line. And we're going to plug in our test point of 0, 0. 0 is greater than 0 minus 4. 0 is greater than negative 4 is true. And so therefore 0 represents, 0, 0 represents a solution. And so you see me shading on that side because that's where 0, 0 lies. Okay, the next line, new color, y-intercept of 3. A negative 1 for slope. So down 1 over 1. And this time the line is solid. So I can do that. There's my line. And now we're going to do another test point. Let's keep with 0, 0. So 0 less than or equal to 0 plus 3. 0 less than or equal to 3 is true. So now I'm shading where 0, 0 sits in regard to that line. All right, the third line, y less than or equal to 2x. All right, so I'm going to color that one blue. And that one has a y-intercept of 0, 0, so we can't use that as our test point now because that point lies on the line. Slope of 2 up 2 over 1. And that is, again, going to be a solid line. Okay. So we cannot use 0, 0, right? So we have to use another point. So I'm going to use 2, 0, okay? And I'm going to color it pink so you can see where it is. See where it is there at 2, 0? So now I'm going to plug it in, 2, 0. So that's going to be 0 less than or equal to 4. So if I plug in the point 2, 0, 2 for x, 0 for y. And that's true, all right? And so that means that we would shade on this side of the blue line. And so you can see the convergence of all of those is this triangular shaped region right here. And that is the solution set. So it's really important that you clearly mark the solution set so that I can tell when I'm grading. All right, what would it look like if we were graphing nonlinear inequalities? All right. Well, again, we're going to graph them as if they were equalities. Same thing with if there's an underline, it'll be a solid representation of the graph versus a dashed. All right, so we'll start with the first one, which is y greater than or equal to x squared minus 1. So that's your quadratic parent function, translated down 1. And we're going to get a little more definition to that. So let's plug in 1 for x, and you get 0. Plug in -1, you get 0. Plug in 2, you get 3. -2, you get 3. This is going to be a solid because it's y greater than or equal to. All right, now, to shade, we need a test point. We can choose 0, 0 because it's sitting right there in the inner region of the parabola. So I'm going to plug in 0, 0. So 0 greater than or equal to 0 minus 1. 0 greater than or equal to -1 is true, which means I will shade in the inner region of that parabola. If that were not true, I would have shaded outside of the parabola. Okay, now we're going to graph the line. So for the line, we need to get it in proper form. So that's going to be y less than or equal to x plus 1. I move that x over to the other side. So that's a y-intercept of 1 and a slope of 1. And again, that is a solid line. All right, we can still use 0, 0 as our test point because the line doesn't pass through 0, 0. And so that will be 0 plus 0 is less than or equal to 1. 0 less than or equal to 1 is true. So that means we're shading below the line because that's where the test point was. So when the test point is true, you shade in the direction of the test point. So where is our solution? Well, our solution is going to be below that line, but inside of the parabola. So it's this region right here, this tiny little section. All right? And that is the end of the first lesson.